As I mentioned, large-scale systems can fail often, and this can really severely affect large or long-running jobs. And some of the largest systems like Kraken, if I'm using hundreds or thousands of processors, I need to checkpoint several times an hour to make sure that I don't have to back up and lose a lot of work if there's a system failure. And it's very expensive to restart computation from the beginning. So just as a note, as you're working in your codes, think about checkpointing early on in the life cycle of your application. It's really important. And as I mentioned, this technique that's used to frequently save critical program data is called checkpointing. And I'm going to give you some guidance about how frequently to checkpoint, which is if you're using a larger system, when you do a checkpoint operation, it takes a certain amount of time to save all that data to disk. Okay? So if I've got a parallel application that's it's using 1,000 processors, I suddenly need to dump, let's say like 500 megabytes of data times 1,000 on a parallel file system. It's a huge load. So it takes time to do that. So one of the questions is, if I know the mean time to interrupt or mean time to failure of a node, how frequently should I checkpoint to make sure I don't waste time checkpointing too often, or take a risk of not checkpointing often enough? So there's a great paper by Daly that talks about this. This is a good kind of rough equation to use, where if you know the mean time to interrupt and the time required to write a checkpoint file, you can compute the optimum compute time between checkpoints. So I'm letting you know about this now, so as you work in your applications, you can think about it early in the life cycle of your applications. So as I said, there's research exploring alternative methods of performing checkpoint. One system-level checkpoint, which is VLCR, MPI-level checkpointing, and then VM-level checkpointing. And the idea behind that is to periodically save the VM state, and then or live migrate the virtual machine from sick to healthier systems. So I've done some work of that at OpenVZ, and it seems to work pretty well. So as I said, at a minimum, structure your code early in its life cycle, so you can periodically save the current state of the computation and develop a capability to restart computation if that saved state of your program is restarted. Okay? Any questions so far? No? Okay. So I want to talk about, give you an overview of virtualization technologies. Has anyone used virtualization yet? A few people. So who's used VMware? How about KVM? And how about Zen? All right. So virtualization is a technique that separates the operating system from the physical computer hardware, and it interposes a layer of controlling software called a hypervisor between the hardware and the operating system. So Goldberg defines two types of virtualization systems. Type 1 is where the hypervisor between the bare metal hardware and the guest operating system. So if I get a server out of the box from Dell and I install VMware ESX on it, I'm putting on a Type 1 hypervisor. Okay? Type 2 hypervisor is actually a hypervisor between the host operating system and guest operating system. So example of that is VMware Workstation or Oracle VirtualBox. So if I take my Windows laptop and I install an application that's VMware Workstation, or I install Oracle VirtualBox, I'm using a Type 2 hypervisor. Okay? So some examples of Type 1 are Zen, KVM, VMware, and OpenVZ. OpenVZ is a little bit different. I'll talk about it. And Type 2 examples are VirtualBox, VMware Workstation, and Parallels for the Mac. So you can get virtualization software for the Mac as well. So in the Type 1 virtualization space, VMware is, I used it a lot. It's been out for a long time. It's a really high quality commercial product. We use it very extensively for NICE. It's very useful. We used it, we had to transition the IT infrastructure from San Diego Supercomputer Center to Purdue for the NICE project. We had a really limited time for transitioning all the IT over. So we took all the machines and containerized them as VMs. And we actually had one server that we couldn't replicate, and we just cloned it across the internet from San Diego in like 12 hours. It worked really well. And so what we're able to do then is be able, one thing we could do is we could create the VM images, and we could also save and archive the VM images of the IT infrastructure we transitioned over from San Diego. So today, if you ask me, there was this feature in NICE Central that was there 5 years ago. I could bring up the VM, boot it back up, and we can go and take a look at it. Okay? This is one of the cool features of virtualization, is just as you can archive and curate data, you now can also archive and curate the virtualization system in which your software can run. Okay, so think of it as like a software tree. You can now create versions of VMs. In Windows, there's a version called Hyper-V. I haven't used Hyper-V, so I can't really speak to it. So here's an example of, we use the VMware infrastructure for the NICE project. Here's just showing you just a snapshot of the VMs we're using today. This is about half of them, I think. So we have a lot of VMs on just a few servers, and it's a very efficient piece of hardware. So if you look at type 1 virtualization, the virtualization systems available for Linux are Zen and KVM. And those are both open source virtualizations based on Linux. Zen was the first version that came out about 2003. It was older, and it seems to be less reliable when I've used it. KVM is kernel-based virtual machine. It's newer. It's supported by Red Hat 6. It's built in. You can get Red Hat 6 support, which makes it really useful. OpenVZ is another one called a container-based virtualization system. I'll talk about it a little bit. So Zen is integrated into the Linux kernel. It uses something called paravirtualization, in which the guest OS runs a modified operating system to interact with a hypervisor. And it's a little different from VMware, where VMware uses a custom kernel you load on bare hardware. Zen is kind of built into the OS of the Linux version that you use. And the host operating system runs what's called domain 0, and the guest operating systems run other domains. Used to be supported in a limited form in Red Hat and Ubuntu, but it's been pretty much replaced with KVM now, and Citrix has a commercial version. So my personal experience with Zen is I spent a lot of time a couple summers ago really digging into these systems and saying, do they actually work? And what I found with Zen is that it worked okay for simple virtualization, but if I tried anything complex like live migration, it just didn't work very well. And I heard there's supposed to be a commercial version that's better, but if I want a commercial version, I'll just go get VMware because it's really well supported. That's my. Does anyone here use Zen? Any good experiences with it? No one? All right. So KVM is the other one, type 1 hypervisor. It's built into a Linux kernel. It's supported by Red Hat. It's more recent than Zen. And it uses a virtual processor emulator called QEMU, which when I first looked at it, I was like, oh, that's kind of weird. It's going to be kind of slow. And then I realized you could actually emulate CPU architectures other than Intel, which gives you a lot of freedom. Some research I'm doing right now is we're actually doing synthetic fault injection into a QEMU emulated processor for looking how VMs would be affected by hardware faults. It's pretty cool. It also supports a wide variety of guest operating systems. I've done Windows, I haven't done Solaris yet, and provides a useful set of management utilities, Virtual Machine Manager and Convert. I'll talk a little bit more about that later. So OpenVZ is another system. It's a container-based virtualization system. So think of it as a secure, isolated Linux container. And it's kind of like a cage for an application running an OpenVZ container. And there's a terminology, virtual private servers or virtual environment. That's what you talk about in OpenVZ. So the two major differences of OpenVZ versus Zen and KVM is that in OpenVZ, the guest OS shares the kernel with the host OS. So if I run virtual machines on OpenVZ, I'm tied to whatever Linux kernel is running on the host OS. Okay. Also, the file system of the guest VMs are visible from the host operating system. So normally with a virtualization system, if I'm using KVM, I have this big, huge file in my host operating system that's a virtual disk drive. The VM uses as though it thinks it's a real disk drive, but it's not. So if I want to make any changes to the VM from the host level, it's pretty much really difficult. I have to actually mount the image as a fake disk and try to get into it. With OpenVZ, you can just CD to the directory that you can see so a subtree of the host file system is the container file system, which makes it really easy to push out software, really easy. Also doesn't use a virtual disk drive, so when you use Zen or KVM, you got these multi-gigabyte images you have to push around, which can take a long time. So OpenVZ can be very fast. So the benefits compared with Zen and KVM, you have very fast container creation, has very fast live migration. It's very easy to modify the container file system, and it scales very well. There's no big virtual disk images you have to push around. The downside is you're tied to the host operating system, Linux kernel version. So that's kind of a downside. So it's good for some things.